guys, welcome back. So today is going to be chapter 4, and it's going to be all about algorithms. We're going to be discussing a number of algorithms. I think in my slides I have 15 or 20, but in the book we have, I think, about 40 ones. Yeah, about 40, maybe 30 something. And the goal is, I think the way I try to split this as the following. The more common ones are in the slides, which are the ones I think that we would need we would benefit a lot from knowing. There's going to be a few exotic ones in the book. I don't think that you would be seeing these a lot. Maybe soon you would, but I don't think that we could use them as easily as we think they are. They're just good to know. So we'll start with the most common ones first, the ones I think or I feel we can use them in multiple problems, different data types. We could use them for a lot of subdomains. And then once we get to the PDF, we'll go over the other ones they could be a little bit specific for certain cases, certain problems, certain data even. And from there, I think it's going to be, I think, something interesting. Because if you can, at all times, if you can have like 4 or 5 algorithms and obviously they'll be good to go. We'll talk more about this like once we get to, I think, later chapters are the ones that are more likely to see as much. So for ML algorithms, as Harry says, where others okay, they find the patterns. So they're all about finding patterns, and the patterns we'll try to find are the ones with the best performance. In this case, best performance is loosely tied up to accuracy. But as we all know by now, accuracy is one thing, and there is many other ways that we can describe the performance of a model. If you think about the pipeline, we're somewhere here. So we have the data, later we have some kind of hypothesis, some kind of questions. We're trying to develop a model. When we develop a model, we find an algorithm, we train it on the data. If it works well, now we have a model. So the ideas I would like to start with is we have a lot of algorithms, a very large number of algorithms. Most of them are general, which means it could be applied to different problems. Some are very specific. Some could be applied to supervised learning, some to unsupervised, some you could apply to both, some are like in semi-supervised, self-supervised. But the overall idea is we have a lot of them. This could be something that could be sometimes a little bit overwhelming because we think that we need to know all of them. I don't think we do. You can think of it like regression. There's many types of regression, but we only use a couple of these. We don't use all of it. It's think of it as a tool. We have a menu, and we have all these things that we could try and use. So for this chapter, things I always would like you to remember is every algorithm you can think of it as maybe as a software. And just like softwares, each one would have its own parameters, settings, and stuff. And you could use them. You could use an algorithm with using the default settings. You could be able to get like very high accuracy, high performance, just by using the default values. Or you could tune it. You could go back to these, parameters and try to change and update them a little bit. There are multiple ways to do this. My preference is simplify. So start with the defaults. We've seen many publications that using the default values actually work very well for our problems. Sometimes it doesn't. So start simple. If it works well, that's good. If you would like to tune, that'll also be an option. We've known the types of learning, and we're going to be covering primarily unsupervised learning and unsupervised learning. Primarily. I will talk a little bit about semi-supervised and the other ones, but the focus for this course is really supervised and supervised. And disclaimer, I'll be like jumping between the slides and the browser because my primary goal actually from this recording is visualization. We would like to visualize how these algorithms work and what they are. Because sometimes the term, when somebody says algorithm, it could be a little vague. So once we see how it works, it actually becomes interesting. So most of my discussion would be actually a description of how these algorithms work in general. We're not going to go too much into the math behind them. Knowing the math is actually good, and my advice is learn how it works descriptive wise, and then go back, and if you find something interesting, try to read about those like math and functions within each algorithm. The way I have this structured, I believe it's in alphabetical order, yes, for the most part. Uh, I really had two options. It's either go alphabetically or go by the most common ones. And alphabetically made sense to put like in on paper. So a neural network or an artificial neural network is an algorithm that's made from layers. So this is what we call a layer. So this is a layer. And this is another layer. And a third layer. Usually at the inputs here, hence input layer, we see the output from here, hence the output layer. And in between all the math happens. You can see here we have hidden layer or layers. The interaction makes a big difference. If you have a hidden layer, this means you have a neural network. If you have multiple, this is what we simply call deep learning. So deep learning is a neural network that has multiple layers. So the way this one works simply is we have the input, we plug in the features input, and we do some math. We don't actually do it. The algorithm does it within the hidden layers. And whatever it predicts something, it sends us like the error back. And we go back and see, okay, how much this error is, what can we do to minimize it? So we start to manipulate those connections or weights to modify them based on the error we have until we get like a very good, outputs, which hopefully matches the data we have. So this is in general, and if you would like to see how it works, there's going to be those linkages or links in my slides. But I believe they're easier to visualize like directly on the browser. So let me show you these. There we go. So this is actually by TensorFlow by Google. They have this very nice visualization. So we have the features here, we have the layers here, and we have the output. So let's say that we would like to do a classification, maybe here a classification study. Here's a number of networks, hidden layers. So we can have in 3 layers, 4 layers, 5, up to 6, I believe. And each layer has neurons. And neurons are the processing units within the layer. So you can see all the connections. And here we can see, do you like to have 50% for training, 50 for testing? We could say, let's have 70 for training, 60 for testing. Let's not have any noise. And let's just run it. And you can see here the model was actually can easily break everything down into 2 classes, class B, blue and orange. Now you can say, well, can I change the learning? So all these are options now. If you change the learning rate, activation function, you will have to regularize, let's say, give this classification. So you can see here we have some funny behavior. If we bring back to none, a different behavior. If we go back to Rilo, a little bit slower, you can see that if we reduce the learning rate, it's much slower, much more constant. Reduce it further, even slower. You increase it, it's different. If we make this regression run, you can see it's very, very funny. It's very funny. Learning rate is very, very high. Let's bring it back. Let's see what we have. Maybe try to reduce neurons, play with neurons. Well, somebody would say, well, how do I do this? Well, you can do it easily by manipulating the functions, but luckily for us, the algorithms do most of this automatically, so we don't have to bother with it. Let's add some noise. You can see the difference between again. Oh, here we go. Now we have much better performance. perfectly match. Let's reduce noise, run again. It's much converges much faster. So this is a very good visualization that you can try and see how it works out. You can show the test results. You can show that you can discretize the stuff, and you can let's see, you can just make it a little bit more complex. You can see the error is different, and then everything converges nicely. And then very easy to visualize. And what sometimes I really like it. So computer science tend to be a little bit flexible than civil engineering, civil environmental. Like if you look here, it says, tinker with a neural network in your browser. Don't worry, you can't break it. We promise. And those light touches makes education and teaching a little bit interesting. The second algorithm that we can think about is a decision tree, and this is it's a very simple algorithm. So it's a tree, and it makes decisions. So it has a tree structure, and each portion of it makes a decision, hence decision tree. And those trees, they're very easy because they're very easy to visualize. So you can have a scenario, and you really have two decisions, class A, class B. Yeah. And then if you go to class A, let's say decision one, then you can have like a consequence A, consequence B. So it could be as easily as class and class, or like item, then decision, so on and so forth. So we call the first node a root. We call these decision nodes, and we call these leaf nodes. This is the end of it. A lot of math also happens there. And to visualize this, I have this. No, let's stop this. I have this of actually. So most of all my visualizations, the one you see here, as well as in the book, I've actually the community was very kind. So they all allowed me to use their visualizations, and this is very hard to make yourself, as you can see. So let's say here we have let's go back. So this is okay. So let's say we have some data. Here we go. So we have some data. Let's say this is I believe this is for houses. So we have it based on elevation, prices, and square feet. So you can split the decision. The further you go down, let's say year built, price per square feet, elevations, and then the more you go, the more you have nodes and leaves and stuff. And then eventually you have all your features included. And you take all this data, and this is what we have. So we have the data here, and you add and start to analyze, and you can see the training accuracy is really high. And you can continue and you finish up. So if you would like to trace, let's say 1 point, you could easily see what are the features that got us to this point, to this prediction. You can easily trace all of this. Like for instance, here you can see, okay, well, this is if your square feet, if the price per square feet is, less than 771, and we go here, elevation is 34 feet. I don't know what RE feet is, but I think this might be like the surface area. And then you move down, and then you move down, and so on. You can easily trace the decision, which becomes interesting. Because in a neural network, it's very hard to visualize those decisions. And in this case, it's a little bit easy. And this is where we start to go from black box, white box kind of things, when we understand what's going on or we don't understand what's going on. But this one is a very easy way so you can see we have class A, class B, this decisions. So for this model here, you can see the training is 100%, the testing is about 90%, which is pretty good. You can always go back to these misclassified ones and see, well, why was this misclassified? Right? You can see all those different types. Tiffany and Tony, thank you for sharing these with us. What else do we have? Yeah, sometimes in my PowerPoint I realize I think it's my computer. It's this desktop. I'm having some of those show up and some don't. But if you just copy the link, if this happens to your device, well, you might have the PDFs. If you have the PDFs, you can just click on the link. If you have, no, you do. You also have the PPTs, the PowerPoints. If this happened on your device, it could be because my PowerPoint is a little bit unupdated. You can just copy the link into a browser, and this should work out nicely. So as we said before, deep learning is a form of an artificial neural network, and there's a lot of different types of deep learning algorithms. One of the things that you might hear a lot are, RNNs and CNNs, so recursive neural networks or convolutional neural networks. Usually they deal with images or text. So if you chat GPT, for instance, a lot of imagery going on there and stuff. The main difference, as we said, a deep learning algorithm has multiple hidden layers. And this could be the same visualization, the one we had from TensorFlow as well. This is a good one. Let's go back to my browser here. Yeah. So Adam Harley actually was kind enough to share this with us. So this is how imagery work out. So if you would like to visualize a deep learning model, it's kind of hard, but hopefully this would work out. You could write here something. Let's say I'm going to write number 3. Okay. So this is my input, and this is how the neural network or the deep learning analyzes my handwriting. So all of these, let's say you could think of them as layers, and they try to understand the pixels, and we go from one to the other one, and then eventually it would say this is the output. So if you look here, you can see that I'm writing a 3, but the first guess is a 9, and the second guess is a 9. So the first guess is 2. I'm sorry. Second guess is 9. You can see the prediction here is 2, which is not correct. So what you could do is maybe the way I drew this was not nice. So let's draw this more nicely. There we go. So this could be, it's between 5 and a 3. The first guess is 5, second guess is 3. My guess is because this is a little bit wider. Let's do something simple. Go for this. So this is 1. You can see I'm writing a 1, and the first guess is a 1. Let me see. Can we do 3? What about this? 3. Okay, between 9 and 3. Is there a way that I can? There we go. There we go. What about now? Okay, 3. Now the first guess is 3. Second guess is 4. So you can actually trace back how each one of those cells, and you have the input weight, and you have the calculation, and you have all those things. So this is how the multiplication between, or the weights between the different neurons and layers. I think if you go back, he also has like multiple ways to visualize neural networks. Let's say put this as 1. So here you can see that how each pixel is actually taken from where. And you go on all the way down to get to 1. You can hide different layers, and you can keep the layers for visualization purposes. I found it very easy to, when we discuss algorithm, to visualize them. I think that, personally, this helped me. This helped me a lot. When it comes to deep learning with text, this is another one that's actually very interesting. So we have different types of algorithm, like an LST or a GRU. But if we go all the way down, yeah, something like this. Let's see if yeah, hopefully, there we go. I don't know, no, go back, go back. This is how autocomplete works. So you start typing a few letters, and then it cannot try to guess what the next letter is. And once you have a word, it tries to guess the next word, and then you have a sentence, and so on and so forth. So you could easily see once you start with P and A and R, then parts, and then the next would be like the most logical thing would be off something. And then here we're gonna have to think about, is it like Africa, Africans, African. There's a lot of cases here, like you can just highlight this context, start with C, because it's just one letter, right? So the words could be can, company code, and then you add O, then country, company, computer, and then you add N, and so on until you get to, like, for instance, once you hit X, it's kind of, there isn't many words that we can go with, context without, being context or constellations. So this is how these things work out. There's a lot of math, and this is, for instance, like an LSTM uh, algorithm. This is how it looks like. Yeah, all these are very good. Here we have those two. Then we move. So artificial intelligence, ANNs, deep learning, decision trees are very common in our case. What's also very common are anything that looks like a tree. So GPT is gradient boosted tree. This is not like GPT, the one from ChatGPT. So this works like a tree as well, and it has multiple variations. I'm sure by now you've heard of XGBoost, LightGBM or LGBM, and CatBoost. These are all different variations to a tree-like algorithm, and the difference is actually very not that large. So give me a second. I'll be back. So, recording. I mean, finding it's becoming challenging. I mean, I'm really sorry about the pause. So let's go back. We were talking about GPTs. Yes, so the goal is we have some data here. Let's say if it's more than 0.5, we go to the left. If it's less than that, we go to the right, and so on. So between XGBoost, LGBM, and CatBoost, these models, I mean, these algorithms are a little bit similar, but they differ in a few things. For instance, if you think about XGBoost, we have an extra space here. We it includes a few techniques to improve its performance. So we have like an approximation process, a histogram process to compute. LightGBM or LGBM is, by Microsoft. It's a little bit faster, could be a little bit faster than XGBoost, but it has like like an internal feature bundling option to accelerate processing time. It's fast, and it's gradient based sampling. CatBoost, I think this was 2017 release or a few years ago. It's also super fast, and it can accumulate categorical values by default. So it's interesting to have and to use. Another algorithm is KNN or K nearest neighbor. So basically, the name gives it up. We're looking for the nearest neighbor for a point to identify it and label it. This one works because you're looking for, if you would like to visualize this, let's say we have here, here, here. Let's say we have this point here that we don't know what is this. Let's add a few points here. We add this. So we're trying to label this question mark. Is it an X or a circle? And we look for the nearest points to it, and from there you can identify. And because we're relying on the nearest point, you're gonna have to find some distances actually. Or one way is to find distance. So you find the distances with all the points nearest to it, and based on that, you can come up with a prediction for this instance. Let me go back to my. Yes, so this is a demo from Stanford. Let's say we're trying to. This is what we have. I would like to use like 4 points or 4 neighbors, and then let's keep this 20 classes, 2 classes. So we have 2 classes, and I'm going to be using 4 points nearest 12 points. So if I'm thinking here, all of these are red, all of these are blue. If I make these 2 points, you can see that the variation becomes a little bit large. If I use 50 points, This would be the easiest one. So this will be called like a borderline. Say 7, much more different. There we go. So for 4 classes. Yeah, now you can see we have different classes. So it could be done for 2 classes or more classes. You could try that as well. Random forest is I would like to say, the natural progression for decision tree. If you have a tree, it's a tree. If you have multiple trees, you have a forest. So how it works is in regression, it actually averages the result of each tree. So let's say you have 5 trees and each one of them gave us a prediction. We average the numerical values to come up with a result for the whole model. If we have classes, then we're going to take the majority vote of each tree, and the majority vote would be the label for this particular point based on the algorithm. Of course, there are other ways that we can, average the results or give the majority vote and do other things with it. So I'm trying really to describe the simplest of the simplest form, just to describe the algorithm. So in this case, you can think about, well, I have this is one tree. I have prediction 1. I have 3, 2, prediction 2, 3, 3, prediction 3, and we have here, this should be decision 3, 3. I usually, if you're a faculty member, I don't think I mentioned this in my first video, but what I normally do in my slides is I keep typos, and if the student finds some typos, they can get points. It's like a participation exercise I do. So I would like to, you can always keep your eyes on something like this. What I normally do is I change the typos every offer, like every year, but I try to keep them, as consistent as possible, like number wise. And this way, if a student, let's say, finds, I don't know, 5 typos, or like 6 typos, then basically the student will have like 1 bonus point towards the end, and anybody else would have like partial points. This can be something, interesting to use. But this is random forest, or if we have multiple trees and we look at each prediction and we try to average it somehow or give the majority of them in a shape or form. SVMs are very old algorithms actually, and they could work out to identify classes very well as regression problems, but much more basically. The goal was to classify things. So we think about a plane, and then we have these are the support vectors, by the way. So this is where the support vectors are, the dashed lines, and we have a hyperplane, and we try to push the points as far as the classes as far away as possible to make the prediction very clear. This is really the goal of an SVM. And we have this, we have this here too, but I feel this is a little bit small, so let's go back to my browser. So highlight support vectors. Let's see what we have here. Let's see, we have a few here, and then we have a few there. So you can see it's a clear distinction or a plane. Now let's make this a little bit more, and let's make this a little bit harder. So I'm going to be putting some reds here. I'm going to be putting some greens here. So this is what we're trying to do, or this would be the plane with the highest accuracy. If I change this into, let's say, quadratic, so we have different types of plane or radial bases. Exception. Let's see. It would work out. Yeah, it could also have different types of visualization here. This is from Jonas Gritman, by the way. So these are the ones I covered for supervised in class. I also covered a little bit of unsupervised learning ones in class. I don't spend a lot of time with unsupervised, to be honest. But for unsupervised, I mainly focus on anomaly detection. outliers, like clustering, and just a tiny bit on dimension reduction. A tiny bit. So remember, unsupervised is where we have inputs and the outputs are not labeled. So this is what unsupervised is. The easiest one is isolation forest. So it's basically like a tree-like model, and it identifies anomalies by a short path. So if a path is short, it's an anomaly because it doesn't grow as much as the other ones. Because usually trees, you can think about as trees grows, continue to grow. So anomalies are so outliers basically. The concept is they're easy to isolate, and because they're easy to isolate, for instance, in this case here, ends here, so this is an outlier. The other ones continue to grow. So the one that doesn't do what the majority does is an outlier, basically, in this case. We also have LOF, or local outlier factor. And in this case, we're thinking about density. We're not thinking about growth of trees and stuff. So we can think about this for a number of points. Let's say we have this, let's say circle or sphere, which is this one here. And an outlier would be the point that's outside that density of those items, those data points. That's like a very simple way to put it down. K-means is a cool algorithm too. It clusters by finding out, or it separates data, not for outliers as much as for just like clusters. Clusters could be thought of as classes without labels. So a very easy way to visualize this is actually here. So let's say we have two clusters in this case. And let's see, there we go. So we have this cluster and we have this cluster. And what you could do is you could try to optimize the distances between the clusters. And in this case, we really have only two iterations. If we say 5, see how many iterations it would take us to get to the optimal structure. So this iteration 1, we have a position of 156. And you continue 557, only 1, 4, and 0. So this is the most optimal thing we can get. If we could add 3 clusters, 4 clusters, 5 clusters, and so on and so forth. There we go. Becomes a little bit much more complex. There. As you can see with clustering, it's interesting because in clustering, when we have the data unlabeled or the outputs unlabeled, we don't know how many clusters we have. I mean, if we have a classification problem, then basically we would say, well, oh, no, it's concrete or steel or on time, not on time, or clean or wastewater, something like this. But with clustering, because it's unsupervised, we don't know how many clusters we have. And this is where we're going to have to let the algorithm try a few things and then bring this back, its performance based on, let's say, delta positions or some other metrics. Oh, okay, so I think, second, what did we do? There we go. So in this case, yeah, so I finished in clustering. In class, if you're a faculty member, usually like we spend a lot of time trying different things. So for instance, in this case, I would like to we try different, testing laws, training losses, different legalization, and I spend about maybe 5-10 minutes on each one. Just let the students try, let them report back. I usually pair them with other students, and we try to share what we have learned from changing with these parameters. So if we go back now to the PDF, go over some of the other algorithms that we don't cover in class. We'll be using more of those like in the coding free platforms like Big ML, Data Robot, Data IQ, Exploratory, Clarify in Chapter 6. In about 2 recordings from now, we'll sit down and try those. Yeah, for instance, we have ANFIS. So ANFIS is a multi-layer, so we have multiple layers of somehow of a neural bears a fuzzy interface. Whenever you hear fuzzy, fuzzy is basically an adjective, or it's like saying when we have this term, it has some uncertainty, cold, warm, hot, and we try to mathematically describe it. So there is a lot of math behind emphasis, different architecture as well. In every algorithm, we have the Python package and the R package too, so you can just install those and start playing with it if you're like into the coding side. So we've seen ANNs. Yeah, we've seen those, regression, classification, reanalysis, post-analysis, decision trees. Yeah, we have those. Deep learning. If you're interested in deep learning, well, you have the pioneers right there. But fascinating how many problems this can solve. Okay, so we have these two. I've seen this as well. Okay, GANs. So GANs are generative adversarial networks. So basically, you're gonna have to have two neural networks, and one is trained, and the other one tries to mimic it, and they contrast and compare. And a very good visualization is actually, we do have one for it. There we go. It's, I think that this is from Georgia Tech, I believe. Yep, Kong. So for this one here, you could say, I have, I'm sorry, I have this is the first model, and I have this data that the second model is trying to mimic. And after many iterations, you would see that everything they would match. You can see the real data here, the big data there. You can see we have some noise, and they try to match up. And once they match, basically, when we have now a neural network that can mimic the actual data that we have, and this one can take some time. We're almost there. You can see the errors here, divergence, convergence. And the more we try to converge, the more it takes a little bit just time to get things done. Yep. Yeah, almost aligning. You can easily see the arrows now is very small. You could try different data types. I believe you could also draw your own shape. This. You can apply this and you can try, and it might take a while. It might take a while to get in, but it does it. You could use a pre-trained model as well to make things a little bit faster. You don't have to see gradients. You can see gradients. Uh, there we go. We also have generalized models. So generalized models can fall into GLMs, generalized linear models. So we have the linear component there. It's not like linear regression though. And we have GAMs, and GAMs are generalized additive models. So it's a model that we continue to add into it. So if we think of a very complex function, we try to get smaller models and we add everything up until we can confine the whole thing. And the bottom line for both of these, we're trying to minimize errors really by defining a model in terms of smooth functions, something like, yeah, I think this one took 7,000 runs to get this line correctly. Yep, something like this. We try to have function instead of, for instance, beta 1 x, we have function now. It's no longer like a parameter slash. And we could also have interactions, and this is where GAMs become GA2M. 2 is for interaction. Yep, something like this. We have, let's say, a straight line, and it's a linear regression, and we have GAMs and GLMs and GEMs trying to define this data. We also have genetic algorithms, can be a little bit complex for new, I would say new maybe learners a little bit because these are based on population. So these are meta heuristics, which means you have a population of solutions and you're trying to use these or identify which subpopulation can actually describe the data that you have. They're a little bit older. John Holland, of course, made these. And you can visualize them. It's very hard to visualize actually, but let's try this. Imagine that you have a space and the space has functions in sine, cosines, plus, addition, multiplication, logs. You're searching that space to identify a function or a mathematical expression that can fit the data. So when you think about linear regression or any form of regression, the function itself is given. So beta 1 x1 plus beta 2 x2. This is given to you. So what you're looking for some values for these slopes. In meta-heuristics, you're not really looking for values for slopes, you're looking for values for a slope plus the form itself. Is it like sine plus something or cosine over tan something? It's no longer just the numbers, you're also looking for the form, which is actually very important because in a way, if you can find such a form, this could be a new equation that you haven't seen before that has the fittest solution. There is a lot of talk here about fitness of the survival over the fittest. We also have GBs, genetic programming. This is when we create programs to instead of equations. We've talked about GBTs. A graph neural GNN. So graphs, right? Visualization for it here. So a graph is basically anything that you can convey in a graph if you can think of a transportation network. In chemistry, this could be like the molecular compound, and you start to add a component to it. And you can see here how does the prediction change. Sometimes you could make it complex. And you can change, let's say, the model accuracy 74%. I've seen this done. If you take, let's say, known compounds with their properties and you train a model, I think DeepMind from Google did this. You can actually identify new compounds just because you have all this data that you can figure out. And this could also be something like an urban planning, for instance. If you do urban planning, so you have different cities and you want to design a new city. So out of the cities that you have, you could be able to have a project where a city with the goal of having like least disruptions or least crowdness to the transportation. So yeah, we could draw. Yeah, we can play with these a little bit. You could also reset it, and it's gonna go from there. So GNNs are interesting. Yeah, heuristics, meta-heuristics, some a little bit closer to genetic algorithm, but you have to realize that there is a lot of these things. They stem a lot of features from actually things we see from nature, ant colony optimization, particle swarm optimization, gray wolf optimization. A lot of features we have in genetic algorithms or population base or differential evolution, or the way that animals sometimes behave or hunt, bat algorithm, bacterial foraging, wind-driven, gravitational forces, black hole algorithm. There's many examples. You see them a lot in optimization problems, whether it's single optimization or multi-optimization. And then we've seen these are the different distances that somebody could use to identify the closest, let's say, class for a point. Linear regression, of course, is another one, simple one. Logistic, we've seen that one too. LSTM, we've seen those. So these ones, LSTMs, anything that has a star into it, like we said before, this might be left best for like a grad course, uh, for students who have a little bit more time on their hands to experiment with these. Random forest, naive Bayes, RF, SPMs, we've seen those. So flow, transformers, yeah, these are a little bit on the advanced side. I would rather not go there now. IF, LOF, we've seen those. Yeah, this is we haven't seen. So shared Duraceq ESD, it's an algorithm that includes a lot of time series. For instance, seasonal trends. It was actually developed by Twitter, formerly now it's X. Uh, it's amazing how the title and the name has changed in very few months. I think Facebook has their own one too. DBScan is another clustering algorithm. Fuzzy scan, fuzzy clustering, or fuzzy C-means. You have K-means, you have C-means, you have fuzzy C-means. A lot of different ways to visualize these. Hierarchical HC, also a clustering algorithm. Okay. Take us a few iterations to get this one done. PC for the emission introduction. We have a lot of features. We're trying to minimize these. Uh, let's see. I think I might have a visualization for this too. Okay, means we've seen. We saw. Yeah. So, for instance, if you have a original data, you try to move it, try to play with it, and you can see the output also changes. So if the data is actually close to each other, you're not losing much. But once the data starts to be much larger, you start to lose a lot, and then you can also have it in 3D. Yeah. This was I think this is by Victor Font. Mm. Yep, and then these are the algorithms. You can see there is a lot of algorithms. My preference is really to maybe focus on decision trees, GPTs, neural networks. If you have these on hand, there's a very good chance you'll be able to solve a lot of the regression problems, a lot of the classification problems. If you want to go for anomalies, maybe IF is easy to use. Clustering, K-means is very easy to. You could try the heuristics or other ones as well, but if you would like to summarize decision trees, random forest, GPTs would be great. You can see a lot of it. If you go to seminars and stuff, you can see many of the other algorithms. We have a few questions and references. Next chapter is going to be, I think, performance metric. Yeah, performance metrics. Well, I'll see you soon, guys. See you next time. Thank you very much.